Welcome back, students, to another video lesson from the chapter Structure of the Atom. Today we shall discuss at first the topic how are electrons distributed in different orbits, or what are called shells. We have studied in our previous classes that atoms of different elements differ in their atomic numbers as well as the mass numbers. Therefore, they have also different number of electrons. These electrons are distributed in the various energy shells or energy levels, which were named by Bohr as K, L, M, N, and so on. This distribution of electrons in the energy shells is known as electronic configuration. It is based on certain guidelines or rules given by Bohr and Bury. This is known as the Bohr-Bury scheme. Let us discuss what this scheme is all about. According to this scheme, the maximum number of electrons which can be present in a particular energy shell of an atom is given by 2n square. Here, n is the number of the energy shell or energy levels. Now, using this formula, we can find out the number of electrons present in each shell. Let us find out the number of electrons present in the first 4 shells. As you can see in this picture, in the K shell there are 2 electrons, in the L shell there are 8 electrons, in the M shell there are 18 electrons, and in the N shell there are 32 electrons. So how this can be found? For n equal to 1, using the formula 2n square, putting n equal to 1, we get number of electrons as 2. For n equal to 2 for the L shell, 2n square, this means 2 into 2 square, that will give us 8 electrons. For the third orbit, similarly we get 18 electrons, and for the fourth orbit we get number of electrons as 32. The outermost energy shell in an atom cannot have more than 8 electrons, even if it has a capacity to take up more electrons according to first rule. According to this postulate, fourth energy shell is expected to have 32 electrons, but since it happens to be the outermost shell, therefore it cannot have more than 8 electrons. Okay. Now, right now, as you can see in this picture, it has been shown that there are 2 orbits. So, in the first orbit there are 2 electrons, in the second orbit there are 8 electrons. Suppose we had a third orbit. In that case, in the third orbit also, the maximum number of electrons that could have been accommodated would be 8. Even though, according to rule number 1, the third orbit can accommodate 18 electrons. But if it is the outermost orbit, then it can accommodate only 8 electrons. So this means straight away that it is not at all necessary for a given shell to complete itself before another shell starts forming. So as a rule, the new shell is formed as soon as the outermost shell acquires 8 electrons. For example, say we consider the element potassium, which has the atomic number 19. Then what should be the electronic configuration? It would be 2, 8, 9. But actually it is not so. The third shell, which is the outermost shell in this case, cannot have 9 electrons. It cannot have more than 8 electrons. Therefore, the fourth shell builds up as soon as the third shell acquires 8 electrons. So actual electronic configuration is not this one, it is actually 2881. This is the actual electronic configuration for potassium. Right now on your screen you can see the electronic configuration for the first 20 elements, starting from hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and finally calcium. This is how the electrons are distributed. You can count the number of orbits in each case, and the distribution of electrons is also shown in the brackets in each case. The same thing can be understood in a tabulated form using this picture. Now the question arises, what is valency? We have understood the electronic configuration of the first couple of elements on the basis of Bohr-Bury scheme. Now out of these, if we check helium, neon and argon, they have the maximum number of permissible electrons in their outermost shell. In case of helium it is 2, in case of neon it is 8 in the second shell, in case of argon in the third shell it is 8. The atoms of these elements are regarded as stable atoms because they have maximum number of permissible electrons based on certain rules. But the question arises, what about the other elements? Their atoms have incomplete outermost shell. Incomplete outermost shell, and have urge or desire to complete this. For this, they approach or invite the atoms of other elements to combine with them. This is also known as chemical combination. The purpose behind this combination is to have either 2 or 8 electrons in their outermost shell. For example, say hydrogen, which has only 1 electron in the K shell, and it needs 1 more to have 2 electrons in the K shell. Lithium, which has 3 electrons in total, it intends to lose 1 electron to only have 2 electrons in the K shell. Magnesium, which has in total 12 electrons, it wants to lose the last 2 electrons so that it may be left with only 2 shells. Thus, we can conclude that with exceptions of helium, neon or argon, the atoms of the rest of the elements have incomplete outermost shells. So in order to complete this, they combine with the atoms of other elements. This combining capacity of an element is known as valency. So we may define valency of elements as the combining capacity of its atom with atoms of other elements in order to acquire 8 electrons or 2 electrons in some exceptional cases. The elements helium, neon and argon have 0 valencies since their atoms have no desire to take part in chemical combination. These are quite inert towards combining with other atoms. So these are known as inert atoms, and the corresponding elements are also inert elements. Relation between valency and valence electrons. The atoms of the elements can normally take part in chemical combination in 2 ways. The atoms having 1, 2 or 3 valence electrons normally lose these to the combining atoms and they show valencies of 1, 2 or 3 respectively. Similarly, the atoms having 5, 6 or 7 valence electrons generally take up 3, 2 or 1 electrons respectively from the atoms of the other elements and show valencies of 3, 2 or 1 respectively. On the basis of this discussion, we can further show the electronic configuration of the elements in this manner. And in each case, based upon the number of electrons present in the last orbit, and the extent by which it is falling short of attaining a stable configuration, we decide what is called the valency. So you can see the valency of some common elements shown in this chart. Now, how we can figure out a relation between valence electrons and chemical properties of elements? In general, chemical properties of the elements are linked with the electrons present in the valence shell. Elements with same number of valence electrons or same valency have similar chemical properties. For example, lithium, sodium and potassium have all one valence electron. In their outermost orbit. So they show valency equal to 1 in their compounds. Elements with either 2 or 8 valence electrons have 0 valency. This means that their atoms neither lose nor gain electrons and are very little chemically active. These are known as noble gas elements. Elements having 1, 2 and 3 valence electrons tend to lose these electrons. These are generally metals. Elements having 5, 6 or 7 valence electrons tend to gain 3, 2 or 1 electrons respectively. So these are non-metals. Elements with 4 valence electrons have the characteristics of both metals and non-metals. These are called semi-metals or metalloids. Both carbon and silicon have 4 valence electrons. Carbon is a non-metal, but silicon is a semi-metal or metalloid.